Howdy, I'm Carlos, and welcome to the beginning of infinity in 1 hour. I read the book like 10 years ago, and it's affected my thinking in a bunch of ways since then. And most importantly, it got me into AGI research 5 years ago. Now I'm interested in taking a Popperian perspective to how the mind works. So that sort of view will inform a lot of what I talk about here as we go through the book. So to start off with, let's talk about a few key mysteries that the beginning of infinity focuses on. The first one I want to talk about is what is just the idea of a beginning of infinity in general, which has to do with certain events in history where progress was sort of unleashed in a big way. Some event that set new things happening. There are three examples to talk about. Things like the advent of life, where before life, there weren't that many chemical reactions, for instance, going on, and life and genetic codes allowed for new proteins and new reactions, really an explosion of them. So that's one narrow way in which we can see before life and after life. This era might represent the number of chemical reactions. Something similar could be said with the arrival of humans, and especially when humans started dealing with ideas in a new way during what's called the Enlightenment. So we'll add that as another example of one of these very unusual and very powerful events in history. So we're curious about these events. What caused them? Why were they so important? And these sorts of things are on par with the Big Bang, arguably. The Big Bang may have brought us all the atoms and physical constituents, but really they're only involved in this very boring intermingling with each other until something like life comes along with ordered information that can cause certain chemical reactions to happen reliably, and so on with everything else here. You don't get rockets until the Enlightenment. The Big Bang won't get you there. So this is really a unique set of events that we need to pay attention to and recognize that they occurred, wonder what caused them, and what made them so special. So all of these are lumped together as forms of beginnings of infinity. There we go. And that's what gives the book its title. So that's the first mystery. The second thing is, if all these events led to an explosion of progress, can that progress continue, or must it end? Are there any limits on it? Either due to genes and what they let us do, or our brains, and are they powerful enough to allow us to continue discovering new things? Or physics. Maybe physics just doesn't allow certain kinds of progress. So we keep making progress until we hit some wall, and then we can't go any further. In each of these cases, there is a intellectual mystery, but there's also a practical value. If we don't know what it is that made our culture so good at making progress at the Enlightenment, we can destroy it. If we don't know what makes humans so special, we might never recreate it. We might never be able to upgrade it. If there are any of these kinds of limits on what we can do, then even if they're far away, we'll eventually hit them, if we're lucky. And so even if the people who haven't yet reached the limit don't care, that's sort of like being a skydiver before you've hit the ground and saying, it's all good. Well, until you hit the ground, it's good. But then sooner or later, when you hit that limit, it's not going to be good. It'll be a disaster. So each of these things is a mystery, but also a practical sort of question. In addition to that, I think there is a mystery that's sort of more or less directly related to this, which is what makes humans so special. So let me try and get this on here. And if we were to draw like a bar chart of, let's say, the number of moon landings for different species, then we'd have a pretty stark picture, because for humans, the answer is something like 10 plus. If you take into account manned missions and unmanned missions and that sort of thing. So that's where humans stand. And then basically, if you took up everything else ever of any kind, any other animal algorithm, it's zero. So that's the everything else category. And that's despite the fact that everything else includes things that have been around for billions of years, but none of them ever made it to the moon. So there's this question, why? Lastly, or I should also say why that's important, which is that if we don't understand what makes humans special, we can never really program it. We would have to just get lucky and somehow do it by accident. But we'd like to understand what makes humans special so that we can put it into our own hardware if we like, and make it have backups and that sort of thing. Basically, I'm saying upload our own brains with backups so you can really never die. That'd be nice. So again, here there's an intellectual question and a practical question. And this is the one that's closest to my heart as someone interested in AGI. So the last thing, well, the fourth little mystery here, big mystery really, is what does it take to do hard searches? By which I mean to find needles in a really, really, really big haystack, which is what it is to, design a rocket, for instance. If we think about a good design for a rocket, that's over here. So this is something, a good something. A good rocket design, good house design, good poem. And really everything else, so much of everything else is just garbage. So finding your way in all that to the good solutions is damn hard. And the number of possibilities is really hard to convey. The number of possible books is just gigantic. And so writing a good one is a tough thing to do. And yet humans do it all the time. And other search processes like biological evolution do it periodically. It takes them a lot longer to do anything good, but they manage to do it somehow. And some processes stand no chance. So I think all these things are related. Humans, I think, are exceptional because of our ability to engage in these hard sorts of searches. And evolution and life and sort of all these things help us. And with the Enlightenment, I think also we began dealing with ideas in a new way that made us better at searching things, more self-critical and that sort of thing. But anyway, this should impress you because the search is really so hard that we managed to ever find anything in practice is unbelievable, really. It's a sort of magic, and yet we do it. And when you try to implement this in a computer and create something that could also make technical and mathematical and physical discoveries, it is really nothing has managed to do that even close. So our mind is doing something very unusual here. It is a real mystery. And as are all these other things. So this should shape the discussion going forward. What is it that caused these really stupendous Big Bang-like events in the history of life and humans and our culture? Can it keep going? Or is there something that will get in the way? What is it that makes us so damn special? Why is it the only species in the many billions of years of history to get to the moon? And nothing else even knows there is a moon. And how is it that anybody, anywhere, humans especially, can find anything in this just gigantic haystack of a search space? These are all real mysteries with real consequences. So with that, I'll leave it there. So now that I've raised these 4 questions, let me try to introduce a few key distinctions. The first will be about what reality allows, just what is possible in reality. Because reality allows many things, but not everything. And that can affect our answers to those 4 questions. And the first thing to note then is that, as I just mentioned, some things are just impossible. Traveling faster than light, creating energy out of nothing. These are impossible things. They can't be done. Meanwhile, other things are possible. I'll give those check mark. And so, everything that humans have so far done is obviously possible. And many other things are possible besides that. All sorts of chemical reactions are possible. Those that don't involve creating matter and energy out of nothing. So those things are possible and we can do them. And the really big question that we ought to ask is, of all the things that are possible, how does that overlap with all the things that are desirable or good? Because if there are all sorts of things that we would like to do, but we can't do them, they don't lie within what's possible, but outside of it, and they're impossible, then that's bad. That means the world doesn't really allow us to do all the things we might want to do. If traveling faster than light was required for most of the things we wanted to do, then we would find ourselves in a rather bad universe, one that didn't allow for much of what we wanted. I think there are arguments to think why that isn't the universe we live in, and so much of what we do want is possible. Meanwhile, many things are possible that we might not care about. These are just bad things that aren't worth doing. So anyway, we'll want to avoid most of those things. But this central bit is the mystery. So next kind of question is, of all the things that are possible, how many are there? How big is the space of possibilities? Is it finite? Can we just do everything and then run out? I'll give this an n to represent a sort of finite number. Or are the possibilities infinite? And of course, in a book called The Beginning of Infinity, you hope to find arguments for why it's infinite. So the possibilities might be infinite or finite in a few different ways, actually. We might have, for instance, an infinite number of steps that we can compute with. So we can imagine that as being, if we're at one point in history now and we're moving forward, we could ask whether or not we're going to hit some kind of boundary there where we can't move beyond. Let's say that the computer of the universe is allowed to run for 1 million steps, and at some point it just stops, and we can't go beyond that. Or is it the case that we can continue, and there's no necessary limit on the number of steps we can take, or the amount of matter and energy available? So we'll call that, storage. The amount of computation we can perform and how much data and information we can bring to bear. Because if you can take another step, but you'll forget something, then that means you can't really make indefinite progress. You can't continue learning new things and adding them to your library. Your library, if it got capped out at some point where you couldn't improve it, couldn't increase it, that would be a limit. So we want to be able to not only take more steps, but increase the size of our library of knowledge indefinitely. So those are two forms of infinity that we should hope are possible. And they're models of physics and the broader universe that mean that the universe collapses and we end up with only a finite set of possible steps we could take. And other models of cosmology allow us to have an infinite number of steps and storage. Those are open questions at this point, but we should hope for infinities there. Otherwise, we'll hit some stage where no further progress is possible. Either no new storage is possible or no new computational steps, no new thinking is possible. Even if we had those, though, that wouldn't be enough for everything that we would care about. We also want, good things to think about and to do. And just because you can take another step doesn't mean that there's another, pile of gold out there to be discovered. You want there to be real opportunities out there that can continue to be discovered. And again, there's no necessarily, I'm not sure we have a hardcore proof that that set of things is infinite, but I think there are reasons to suspect that it is, and that no matter what state of knowledge we reach, that there will be problems within that set of things, and therefore opportunities that consist of solving those confusions. So there are reasons to suspect that that set might be infinite, even if there isn't a hardcore proof at this point. But this is all part of the broader question of what reality allows. Does it allow all the things we would care about, all the things we would want to have? Is the set of possibilities finite so we can run out, or is it infinite? There are various ways in which it could be finite, infinite. So that is, again, all about what reality allows. But there's a second and equally important question, which is not just about what reality allows, but what particular systems can do. Systems like you and me, or our society, or animals and AIs. Each of these systems may find itself being extremely powerful or not so much. So if we think about everything that reality allows, the set of things a particular system could do might be less than that, in which case we might say it's, in some sense, incomplete. The set of things it can do is less than all the set of things that are possible. So that might be incomplete or non-universal. In contrast, a system might be complete. Of all the things that are possible to be done, that all of the things that reality allows, this system can do all of them. It has an equal repertoire to what reality allows. So we would say that is complete or universal. Now, that kind of system is arguably what we are. And the way to think about this is to say, again, if we imagine all the things that are possible, is a particular system limited to some small subset of those things that are possible? This is like most animals, for instance. If you consider a special case of like all the chemical reactions that are possible, any given organism really only has the knowledge to do some of these and can't discover more necessarily. So it would have a smaller repertoire than all the things that are possible. Meanwhile, maybe there is a system that could eventually do anything. And that would be a universal system, this complete system. And hopefully this is what humans are. And that's what the book argues. So we would say humans and people more generally, whether they're humans or AGIs or aliens, whatever. And over here, we have all these kind of special purpose systems. AIs, animals, and so on. So they have a limited set of things they can do. Now, it should be noted that any given system is going to be always finite at some point. So, it can grow, and that's key to its being able to improve and so on. But it won't in fact do everything necessarily, but it can do more and more and more in an unlimited way. And these other systems might have constraints on them, so they can never really move beyond a certain point, no matter how long you let them. I mean, we've let certain species exist on this planet for billions of years, and they had not gotten to the moon. So you see, we're starting to connect with some of those initial questions I raised. But anyway, this hopefully provides a bit of a broader framework of going beyond just the initial questions and kind of turning them into some of these other key questions and showing some key distinctions. So question number 1, what does reality allow? And question number 2, what can particular systems do? Because if reality allows a great deal of things, but any given system can only do a small subset of them, then that is still going to be a weak system. It won't be physics' fault that system can't do much. Whereas humans can evidently, so the book argues, do anything that is possible, eventually, if they have the right knowledge, and so on. But these are hopefully some key distinctions that we'll be able to make use of later on. So thanks for that. So if reality allows for many possibilities and some systems are capable of taking advantage of more of that or less, how do they do so? And the first thing to note is that they need knowledge. And knowledge has 2 jobs. The first of which is to make specific things happen. So if many things are possible, but only some are desirable, then you want to make the desirable things happen and not the undesirable ones. So how does that work? I think a simple example to keep in mind would be something like trying to get a specific sequence of heads and tails with a coin. To start off with, let's just imagine like one coin flip and the probability of getting either heads or tails. So here's our probability. And in the first case, we would just have a 50-50 shot. of either. Suppose what you want, though, is just heads. I want to be able to flip a coin, or rather, I want to see on a table a coin that's heads. And if I just flip, I have a 50-50 shot of either. That's sort of like, we'll imagine that being sort of a spontaneous process. I'm relying on this just some randomness to produce the result here. I'm not controlling the result. So that's a spontaneous approach to getting what I want. I want heads. And the way I'm getting it is with this sort of random flipping. So that's one way you can try to get what you want in the world. Another way would be to try something more of a controlled process. So what would that look like? Well, in this case, you could just tell me, I would like it to be heads. And I could just take the coin and put it down as heads. That would have a near perfect probability of getting what you wanted. So if we imagine that one, now we have heads and tails. And here's 100% basically. And if you just told me to put it down heads, I could just put it down heads. And there'd be very little chance that I would somehow misread what's happening and put it down tails. That's the effect of you basically telling me what you want and me having the ability to distinguish between heads and tails and what you told me. And then also being able to distinguish between heads and tails and the result and being able to change the result if it's wrong. That is a general thing that knowledge can do. It can basically take the things you don't want, in this case, tails, and make them not happen. And then take the thing you do want and make it much more likely to happen. And it's a little bit of a silly case when we're talking about like one coin. But if you imagine trying to get a particular sequence of coins to land on a table, there was like 100 coin flips in a row. You said, I want it to be heads, 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 tails, tails, tails. Let's see what that would look like. So if we have a new situation here where instead of doing just heads or tails, let's imagine I want to see a very specific sequence of heads and tails. Heads, 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 tails, 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 heads, tails, heads, tails, heads, tails. If we go back to a spontaneous process now, the likelihood of us getting this particular sequence is very, very low. And there's a whole bunch of other sequences too that have equal probability. That's also very low. But if this is the one that I want, I could just tell you that. And again, if we have the right information in place, that's been written out as it has been here, I can just, again, use my hand, read the paper, make sure it has the right result, and do it again and again and again, till I have the right result here. So with the right information in the right situation, I can have basically 100% chance of getting exactly the result that I wanted. That's the sort of thing that knowledge can do in general. This is a dumb example with heads and tails, but the same thing would apply to producing a very specific protein or whatever. The specific sequence of things needs to happen. And if the right information is present there, the right things can happen at every one of those steps. And if that information isn't there, then any number of those different steps could happen. And you would get this one or this one or this one or this one, rather than the one you wanted. So anyway, that's one of the jobs of knowledge when it comes to getting things that are possible in physics. The second role of knowledge is not to make specific things happen, but something a bit more indirect than that, which is to sort of capture patterns in reality. So there are all sorts of patterns in reality, regularities. Gravity is one of them. The fact that the sun rises every day. There are all sorts of patterns you could exploit. I'm a person, I have a pretty similar personality from day to day. If you know that about me and about people in general, that will help you. You won't see me tomorrow and be surprised at everything I do because you recalled certain aspects of who I am, and it's helped you predict what I'll do next day. I like Norm Macdonald. I'll probably make another Norm Macdonald joke. That's not going to surprise you if you know me. That's a pattern in reality among many. So we can imagine there being particular objects, real objects out in the world, people, planets, you name it. And then we can imagine, a mind over here and having sort of some representation of that object in the brain. So this is sort of, an idea. And if we play our cards right, we can get there to be sort of a correspondence between these different things. The real object and the idea about it can become similar in some way. And if you do that, you can get several advantages. In terms of, for instance, it can be fast. If this is some distant object, I'm thinking about it, some kind of very distant thing, I can maybe think about how I would interact with it. Let's say this is the car in the garage, and I don't want to go out to the garage, but I can imagine what would happen if I did go there. I just want to stay in bed. So if that's what's happening, if this is an accurate model of the car, I can just think about it and get the right answer. What I need to do to the car, what I left in the car, something about the car, and this will be an accurate representation. If it's not, then it won't be very useful to me. But this allows me to avoid the work of actually going to the car or actually picking up some heavy object or whatever. My computations about the object can be much faster than interacting with the object itself. Perhaps more importantly even, it can be safe to operate on these ideas rather than the actual objects. If this is a tiger, then I will do better to think about how I might handle the tiger sort of theoretically in my head before actually going out to do something with a tiger in real life where I might get eaten. So the chances of getting eaten when thinking about the tiger are pretty low. You can do more with patterns in reality than just capture a small thing like a one object. You can also capture much larger patterns. So if this is a particular idea, and here is the whole of reality, then you can imagine catching some small pattern, like I said, just about me, let's say, as a person, or about tigers. Now, there may be a lot of tigers, or there may not be, but there are probably only tigers on this planet. And so all of reality is much larger than just this planet and its tigers. Nevertheless, it's useful to know about them. So you can have an idea which applies to all tigers. And that would be sort of a small pattern in reality. Meanwhile, if you know about gravity, let's say, that could extend through all space-time and cover all of reality on every planet forever and ever and ever. And that would be a sort of a universal pattern. So that's the sort of thing which we could capture with the right knowledge. There are these larger patterns in reality, and the right ideas will capture them. So overall, if we zoom out now, we can start to see some of the roles of knowledge. If many things are possible, some of them are desirable, the question then becomes, how do you get those desirable things? And this shows you with coin flips as kind of a stand-in for, sequences of steps more generally, that knowledge can make the right things happen and make the things you don't want to have happen not happen. And somewhat more indirectly, you can have huge advantages in how you deal with ideas and objects if you have a little bit of indirectness here. You have a representation in your head of an object out there. Or if you capture some aspect of reality over here that may be infinite. And so if you know about this universal pattern, there's a lot of things you don't have to try in reality. You already know that if you pick something up, it's going to fall down. Things like that. You don't have to actually go out and do it. And so it can factor in your thinking and help make you much, much more efficient in terms of figuring out what would work and what wouldn't work when you're trying to achieve the things you want to achieve over here. But anyway, those are the two roles of knowledge in helping you make things happen and capture patterns in reality. And by the way, this is what Deutsch would call explanatory knowledge, knowledge which reflects the things that are really out there and how they really behave. So if reality allows many things and the way to get the things you want is with knowledge, how do you get knowledge? So let's attack this question from saying, suppose you have some amount of knowledge or some kind of stuff you can work with. How do you get more knowledge? So this is your currently existing knowledge or just existing things in general. how do you get from that to, let's say, new things? You got squares, circles, stars, triangles, all sorts of things. How do you go from those existing things to new things? Well, in biology and really everywhere, you need some process that we'll just call variation. I almost like to think of it as this diverging funnel, because you start off with a few things and you end up with many things. It's often kind of just a messy sort of process, a bit random. So that's variation. You could call that conjecture or coming up with new ideas. But fundamentally, you need some source of novelty, of new things. It doesn't have to be perfect. It doesn't have to generate only improvements. Hopefully, some of these are improvements. So if we imagine that one of these is an improvement, let's just get a little check mark there. We've generated many things, some of which are worse. This one might be better than what we have currently. That's the only thing this process needs to do, create new things, some of which are better occasionally. And evolution definitely does that. Most of the things it produces in terms of mutations are bad. That's okay, because at least some of them are good. If this process produces nothing that's good, then it won't allow progress. It has to produce some things, at least that are better. But you don't need just that, because if this is all you had, and you just kept taking existing things and making new things, and then making new things out of those, and on and on and on, you would just require so many more resources. It would just be an exponential explosion, because you'd be creating 5 things for every one thing that exists, and doing the same again and again and again. So in practice, you can't do that. You run out of resources. Just a matter of how you end up doing that. So what you need is a way to get rid of the trash and focus all your resources on the good things. So in this case, what we want to do is have some process by which we end up with this good thing, this square. We'll call that process selection. And it's more of a collapsing funnel sort of thing. Because we start off with many things. At the start of this process, we don't know which ones are good and bad. And then through process of different kinds of filters, in the case of natural selection, you might get eaten. If this is people at a meeting, they might be discussing something and say this is too expensive. Some criteria are applied to distinguish between these things. Some of these are fast animals or slow animals, or costly projects or cheap projects, good products, bad products. And through the process of discussion or empirical test or getting eaten by lions, some of them get weeded out. And we end up with, hopefully, at the end of this process, the good things. Good new things. And like I said, this process is called selection. You can call it what you want. I mean, this is the job of it, though, is to somehow distinguish between what's good and what's bad, and then to cause the good things to remain and the bad ones to either be deleted or simply not affect things very much. You can have bad ideas in your head, but they're not really doing much. And that's the process also of selection. So you can just get rid of them entirely, or you can just sort of suppress their effects so they don't do anything bad. All of this process seems very biological, perhaps, and that is where it originated. So if we think of just Darwin to start, then you'd be right that this is very much a process of evolution. It starts with biology. But what was discovered by Karl Popper, or at least argued most forcefully, was that this is not just about biology. The basic logic here applies to many, many more things. So you could imagine applying to certainly us, humans, and the way we create knowledge, but also, aliens if they exist. Then they have 3 eyes, let's say. Really anything that is producing knowledge, or animals. If you have some kind of animal that learns things throughout its life, it's also going to be trying things and keeping what works according to some kind of inbuilt criteria. And it doesn't apply just to biological things. It would apply to any kind of AI algorithm. just as well. So this is the sort of generalization of Darwin. It says it isn't just about biology. It isn't just about mutation. It isn't just about natural selection. These two processes are fundamental to all knowledge creation. You have to have some way of coming up with new ideas. Hopefully some of them are better. And then that's never enough. You have to have a way of getting rid of the bad ideas and finding which ones are good. And again, this is not just about biology. It's about everything that produces knowledge. Yeah. So not all knowledge creators are equal. That's something you'll notice if you look at biological evolution and compare it to humans. And it's one of the questions I raised at the very beginning. What makes humans so special? Why are we the only species to have landed on the moon, whereas no other species seems to even know it's there? So there are definitely big differences here. It's also the sort of question you might ask of different neural network, machine learning systems. Which ones are better than others? In all of these cases, you have knowledge creating systems that work in different ways, and some of them are better than others. So what makes the difference between the bad ones and the good ones? That is our question here. So we'll have bad and we'll have good. So the first thing we can note is that if knowledge creation depends on variation and selection, let's ask, what are the better and worse forms of variation and selection? So the first thing to note is that the job of variation is to produce new things that are occasionally better. So let's look at two different forms of variation here and ask which ones, what might make one better than another. So suppose we start off with some system where most things, most ideas are bad. I'm thinking more of the human case here where somebody is just very wrong about how the world works. They think it works in terms of witches and gods and so on. Well, most of their ideas about how to make progress in the world will probably be based on those ideas, and those will likewise be pretty bad. One does not build rockets by thinking in terms of spirits and witches. Meanwhile, suppose that you have a normal human brain where more commonly you have some bad ideas, but also many good ones. Well, then the ideas you start to come up with might very often be pretty good. Not all of them. Some of them will still be bad. But you now have a system that, because it started off with fairly good ideas, produces some good ideas. And so what makes the difference here then, what we're looking for in terms of variation, is we want more good ideas. And a system of variation that doesn't produce good ideas ever is no good. It's also not good if you have a system that doesn't produce any variations at all. You just never come up with new ideas at all. That's not good. But anyway, if you're thinking in terms of physics and space-time and forces and so on, these are very good ideas that happen to capture many of the patterns in reality. And so before we even created any ideas, we're starting with very good material. And when it comes to creating new ideas efficiently that are good ideas, part of the battle is getting rid of bad ideas, but part of the battle is just not exploring huge sets of bad ideas in the first place. It just never occurs to you to think in terms of witches and cats, sinking ships, and so on. And thank goodness, because it's a huge waste of time. So when it comes to variation, that's what we want. More good ideas. And we want to never even think of all of the bad ones. What about selection? So the role of selection, again, is to take in a bunch of ideas, some of which are good, and some of which are bad, and hopefully weed out the bad ones. So let's imagine that we have a bunch of bad ideas, but also some good ones. So those are the bad ones. We've created some other ones that are good. At this stage, we don't know what's good and what's bad, and we want our methods of selection to tell us. A bad method of selection wouldn't be able to as reliably. it wouldn't find this good one. It would sort through these with its various filters, and it would miss the good things. So these filters would not be very good. It wouldn't be very sensitive to the right sorts of answers. Meanwhile, a good method of selection would very easily detect, these are the bad ones and this is the good one. So we want here is a very accurate distinction between the good and bad ones. We want to reject bad ideas. We want to sort of catch all the good ones. So to the extent that a method of selection does that, that's what we want. Also, we should hope that it's efficient. We wanted to do those things efficiently. So here I have in mind things like some like quick tests you might run on some idea to say, like, does this make sense at all? We have in the back of our minds, thousands and thousands of ideas. So if I tell you something like, I saw a cat split in two the other day and then walked down the street, this would immediately begin to conflict with other ideas in your head about conservation of mass and what cats can do. It would start to break your notion of what is plausible, or conflict with what you think is plausible. And so it would basically be hitting one of these filters in your head, and you would say, I don't think this idea is right. So you very quickly and very easily be rejecting bad ideas. You wouldn't have to go through some lengthy process to discover that. So we have, in the case of human ideas, some very powerful forms of selection. We can sort of do mental simulations of how things would go. And we can have arguments. And so if you just have a simple rule like, what goes up must come down, if somebody tells you they threw something up and it never came down, you just use that simple sort of logical rule to say, what they said doesn't make any sense. So we can run our own little mental simulations. We can use our own little logical rules. We can perform actual experiments. We can have discussions. All of these ways that we can use to try to figure out which ideas are good, which ones are bad, and do this efficiently and effectively. So that's what makes the difference for selection. And that's part of what distinguishes humans from natural selection, which is much weaker in many ways. As a third thing here, which I'll call attention, and here is something where we sort of diverge between humans and biological evolution very strongly. Because if we think about all the ideas in your head, many of them will be relevant to the situation, and many of them won't be. Or I should say, if I draw an X here for all the irrelevant ideas in some situation, then a good way of dealing with ideas would find out which ones are relevant to your situation and then use those in variation and selection. You'd start combining the right sorts of ideas and testing them in the right sorts of ways. And so one example I like to use is that, if I hit my head on something, I've now confronted a problem that I want to solve. And I could begin thinking about whales and exoplanets and black holes, because those ideas are in my head, but they're like these red X's. They're irrelevant, and they won't help me solve my problem. Whereas I bump my head and start thinking about heads and walls and moving in 3D space, well, now I'm beginning to generate ideas that have a good chance of solving my problem, of avoiding hitting my head again. And I can ask the right sorts of questions to see like where the wall is and whether my mental simulation says, this course of action will not bump my head into the wall again. So a good way of using your ideas would find the relevant ones, and a bad way would not. It would focus on irrelevant ones. And the reason I said earlier that this is where you start to see a distinction between human thinking and biological sort of evolution and the way it produces variation selections is that in biology, the next mutation is not going to be guided by any idea of the situation. There's no separation of mutations into like the relevant ones and the irrelevant ones. If a giraffe needs a taller neck, that fact will not influence the next mutation that happens. The next mutation that happens could make its heart not work anymore. It's just going to be a random mutation that comes up. Meanwhile, in the human case, like I said, if I bump my head, I can begin thinking about exactly that situation, and what I see, what I feel, what I sense, what I think. I can then affect the next mutation, the next thing I try, the next idea that I have. And that's extremely valuable, because if you have billions of places for mutations, almost none of them are going to be the one that will help you as a giraffe evolve a longer neck or solve some problem. And likewise, in the human case, if you have thousands or millions of ideas, most of them will be unhelpful in every circumstance. So if you can focus in on the relevant ones, you'll be much better off. So that's what we want here, is to have ideas which are relevant to the situation. So all these things can make a huge difference in the efficiency and effectiveness of any kind of knowledge creation process. There's one last thing I want to talk about, which is just the notion of knowledge in general, and how, if we consider like the set of all possible ideas, some knowledge systems, some knowledge creating systems can produce any of those ideas. So hopefully in the human case, we just have total ability to think of any possible idea. So if there's some idea that we depend on to solve some problem, some idea about rockets or some idea about space-time, whatever it is, it lies within the set of things that we can think of. Meanwhile, something like genes, the way they're usually interpreted to create proteins, that's a much smaller world. You can't really have ideas about spaceships embedded in DNA. Or if you did, it would be humans that put them there and humans that interpreted that information. The way that information is normally interpreted, it just converts things in DNA into proteins. So you can only express proteins. You can't express ideas about rockets within that system. So that's a much weaker system. It just can't even conceive of the ideas that we can. There's no way for ideas about rockets to arise within that system. So here what we want is something like expressive power. We want a system which can express any idea, which can have any idea. Because that brings more possibilities within reach. And so in each of these cases, we're seeing ways in which biological evolution or AIs or humans, aliens, animals, have different ways of creating ideas, which can be better or worse. Different ways of finding out which ideas are good, that are better and worse. They can become better or worse at figuring out which ideas are relevant to the situation. Keep in mind, every one of these can have make a process millions or billions of times more efficient. And that's why you see us, humans, getting to the moon and everything else having no idea about it. So I wanted to return to the initial mysteries I began with. The hard problem of search. When we have a huge set of possibilities in reality, and many of them are trash, how do we find the good things? How do we find the valid designs for moon rockets in and among all the wrong ways you could build a moon rocket? That's a very, very hard problem. How do you find a good physical theory of general relativity and avoid all of the random theories that are terrible, including just slight variants of that one theory? This is a very difficult problem, but when in the last video, I talked about the different ways in which knowledge creation can be more or less powerful, variation, selection, attention, and different kinds of expressive power. All of those things help with the problem of hard search. Some systems are capable of doing it. That's humans. Most others are not. So even if we haven't solved this problem completely and in detail, I think some of this discussion here will hopefully shed some light on that. And the same thing applies to the question of what makes humans so special in terms of our many moon landings compared to everything else which doesn't know there's a moon even. It's again our ability to do these hard search problems. And that has enabled us to discover all sorts of interesting ways to control reality and also to discover what reality is actually like, what David Deutsch calls explanatory knowledge. All of that has led us to this ability here that nothing else has gained. Nothing else has been able to find these things. They've been stuck in the trash for billions of years. We have what it takes, apparently, to find the good stuff in and among the trash. Again, we don't know exactly what makes humans different. We know some things about it. And none of this is intended, by the way, to say that these mysteries are entirely solved. This program and the book from David Deutsch at the beginning of Infinity hopefully push us much further, or at least offer some helpful tips in terms of how to think about these problems, even if they don't solve them completely in detail. Anyway, the first mystery I started off with, though, was how did these particular events begin? These seeming leaps from nothing much happening to huge, rapid progress. We don't have the full answer to the origin of life or what makes humans special or what exactly about our culture led to this rapid progress. But one thing we can say about it is that in each of these cases, something new happened with regard to knowledge and knowledge creation. Before life, there wasn't really any kind of information that could be like a billion letters long. That's a new kind of thing. And once you have the ability to create large amounts of information and begin tweaking it, now you can produce quite large amounts of complexity. You can produce proteins of many different parts. You can produce many different proteins. And those can collaborate to produce very complex bodies. But if you don't have, if your hard drive in some sense is only 1 bit, that doesn't allow you to encode very much knowledge. Whereas if you have a billion bits, more like evolution has in the case of DNA, well, now you have a lot to work with. You have a lot of memory in which to put bits of things you learn. So something like that is responsible for the origin of life and that huge leap in capabilities. With humans, we see something different where it's more like a growth in the expressive power of things. So now information can refer not just to proteins, but to anything, including black holes and quasars and, kitchen tables, just everything. And then with the Enlightenment, our culture changed in a new way, where one aspect of it is that it was very much more, self-critical. So something about the specific ideas we had about variation and selection and what kinds of areas we put our attention, those were very, very powerful. And so David Deutsch talks about good explanations and other things. These are new kinds of very stringent criteria on what counts as a good idea. And it turns out that if you use those criteria, you have a much more sensitive instrument for rejecting bad ideas and finding the good ones. So anyway, all that is to say, each of these leaps into vast amounts of progress has involved a new kind of knowledge creation, a new relationship with knowledge emerging in reality, with life, humans, and the Enlightenment. But now finally, what about limits? We've seen that reality seems to allow a great deal, could potentially be infinite. And some systems are able to take advantage of it better than others. And one thing to note here is that, humans can do all these search problems. Humans have discovered all sorts of things which have allowed them to get to the moon. That has involved going around and escaping the barriers of our genes and our hands and what we can lift and so on, what we can see. So when we ask this question, are there any limits to the progress we can have? The answer seems to be no. It's not that there are no obstacles, but it does seem like humans can produce, they can discover ways to just get around those obstacles. And so we keep on going up and up and up, hitting new obstacles along the way, but still being able to get across them. One obstacle is, can you lift objects of a certain weight? Can you see photons of a certain wavelength? Those are things we couldn't do, but then we discovered through trial and error exactly how to do those things. And now that we know them, we can do those things, despite the fact we weren't born knowing how to do those things. So there are many, many barriers, many, many problems, but it does seem like we're able to just get over them Maybe not trivially. It could take us 1,000 years to solve any given problem, but it does seem like we can solve them. In which case, nothing about the way that we started off will limit our progress. We can continue discovering new things and evidently overcoming every barrier along the way. So I thought I'd end with two quick points. The first is that the theme of the beginning of infinity, or one theme of it, that focuses on the idea of infinity itself, is that no matter how much progress we make, we'll always be at the beginning of infinity. And that's because no matter what number, for instance, what number you pick, whether it's 1 or 1,000,000 or 1,000 or whatever you like, it's always unusually close to the beginning of infinity. There are always an infinite set of numbers beyond that. So if we think about the view from today, here we are at this point in history with really, an unknown set of things in the future. All sorts of great things, hopefully, that are possible. And here we are very early in history. But if David Deutsch is right, and the set of possibilities is infinite, and this is not just the view from today, but it's the view from every day, no matter how far in the future. We'll still be here wondering and being able to shape what comes after. And that's sort of the view we should have, that it isn't as though we're at the end of history or at the end of something. It's very much the beginning, and perhaps always will be. So that's, I think, a helpful perspective to have here. Secondly, I want to emphasize, I'll just throw an infinity here for good measure. When it comes to thinking about what reality allows, and what systems are capable of exploiting reality and doing more of what it allows, it's worth noting that one perspective you should have about people is that of all the things that reality allows, say you're all possibilities, then only a very small fraction of them will happen spontaneously, or even with life. So that's sort of the spontaneous set of processes that can happen. Things like rocks falling and certain kinds of chemical reactions and so on. But most things can't happen that way. Most things require knowledge to make them happen. So if you want all of that to happen, all of the interesting things that could happen, that requires knowledge. And therefore, really, because only humans are capable of producing knowledge that covers the entire span of what's possible, really this requires not just knowledge, but requires people. So when we think about the future, we see ourselves very much at the beginning. But we also ought to see ourselves as really the window through which most of what can happen in reality actually does happen. We aren't just along for the ride. It's not just that people can do these things and that those things could have happened anyway. It's that, yes, we can do all those things, but also those things could not happen without us. So this is part of why humans, and people more generally, aliens and AGIs, are of cosmic significance. In some ways, if we were to think about the shape of the universe, or if I were to draw another plot at the beginning of infinity, this time just representing all of the things in the universe, just like how interesting is the universe. Well, over time, it might get a little more interesting as you get black holes and other things, new things, but it would be pretty boring until humans or something like us came around. And then you'd see a vast Here's the beginning of infinity with humans. So it's not just that we're taking off and that we're enjoying it, but actually the whole of reality is getting more interesting. There are things that just would not have happened were it not for us. So again, this is part of why humans are cognitively or significant, but cosmically significant. And that seems to be true of all people. There may be differences between us, but we all share this fundamental ability to understand and hopefully discover anything. So with that, I hope you enjoyed it. And of course, there's much I left out of the beginning of infinity. So go and read it.